Spacetime and its fabric. Spacetime is a concept that fuses the three dimensions of space with the one dimension of time into a four-dimensional continuum. Introduced formally in Albert Einstein's theory of general relativity in 1915, this framework revolutionized our understanding of the universe. Rather than seeing space and time as separate, unchanging stages on which the events of the universe play out, general relativity shows us that spacetime itself is dynamic and responsive to the presence of mass and energy. The term, spacetime fabric, is a metaphorical way of describing how this continuum behaves, like a flexible sheet that can be warped or stretched by gravitational forces. The more massive an object, the greater its gravitational pull, and the more it distorts the fabric around it. This distortion is what we perceive as gravity. For example, the Earth orbits the Sun not because it's being pulled by an invisible force, but because the Sun's immense mass has curved spacetime, and the Earth is following a straight path within that curve. Understanding spacetime as a fabric allows us to visualize phenomena such as planetary orbits, time dilation, and gravitational lensing. However, it also introduces a more profound possibility that this fabric can be torn or collapsed under extreme conditions. What does it mean for spacetime to collapse? Does the fabric rip like cloth, or does it buckle inward to a point of infinite density? These questions push the boundaries of modern physics and lead us to phenomena like black holes and cosmic singularities, where known laws of physics break down. To answer them, we need to delve deeper into the curvature of spacetime and what it signifies in extreme environments. Understanding the nature of spacetime curvature and gravity, the curvature of spacetime is not a physical bending like that of rubber or metal, but rather a geometric distortion defined by Einstein's field equations. These equations relate the energy and momentum of matter and radiation to the curvature of spacetime. Essentially, matter tells spacetime how to curve, and curved spacetime tells matter how to move. One of the most profound consequences of this idea is that gravity is not a force in the traditional Newtonian sense, but a result of the geometry of spacetime. The Earth orbits the Sun because it is following a geodesic, the shortest path between 2 points, in curved spacetime. When spacetime is curved mildly, such as near the Earth, we observe everyday gravitational effects. Objects fall, time slows slightly closer to Earth's surface, a fact now accounted for in GPS systems, and light bends subtly when passing near massive bodies. However, when curvature becomes extreme, such as during the collapse of a massive star, something extraordinary happens. The fabric of spacetime can curve so sharply that it pinches off, forming what we know as a black hole. In this scenario, all paths lead inward, and even light cannot escape the resulting gravitational prison. Here, the mathematical models predict a singularity, a point where density becomes infinite and spacetime curvature becomes undefined. This is the most intense form of spacetime collapse currently understood in physics. Conditions under which spacetime fabric can collapse. The collapse of spacetime occurs under extremely specific and violent astrophysical conditions. The most commonly studied scenario is the gravitational collapse of massive stars, particularly those exceeding about 20-25 solar masses. When such a star exhausts its nuclear fuel, the outward pressure that once countered gravity diminishes. As a result, gravity dominates and causes the star's core to collapse. If the mass is sufficient, not even neutron degeneracy pressure, which supports neutron stars, can halt the collapse, and a black hole forms. This is not just a collapse of matter, it is a collapse of spacetime itself. The core contracts to an infinitesimally small point, and the spacetime fabric around it curves infinitely inward. But collapse doesn't only happen at stellar scales. In the early universe, right after the Big Bang, spacetime underwent extreme fluctuations due to extremely high energy densities. The concept of cosmic inflation posits that spacetime expanded exponentially within a fraction of a second. Some cosmologists theorize that regions of spacetime might have collapsed during this phase to create primordial black holes. Tiny black holes form not by stars but by fluctuations in the early universe's energy density. Moreover, quantum fluctuations may have briefly destabilized spacetime in a way that produced wormholes or other exotic structures, though these remain purely theoretical. In particle accelerators or high-energy cosmic collisions, if energy densities become high enough, it's also theorized that mini black holes could momentarily form. Temporary collapses of spacetime, though none have been conclusively observed. Black holes and singularities. Once spacetime collapses into a black hole, we enter a regime where classical physics ceases to function reliably. At the heart of a black hole lies the singularity, a point of infinite curvature where our current understanding of spacetime breaks down. All known laws of physics, including general relativity and quantum mechanics, are unable to describe what happens at this point. It's a literal blind spot in our understanding of reality. Surrounding the singularity is the event horizon, the boundary beyond which no information can escape. As you approach the event horizon, time itself begins to behave differently. To a distant observer, time appears to freeze for an object falling in, while for the object itself, time continues normally. This gravitational time dilation is a direct consequence of the spacetime curvature becoming extreme. But black holes do more than swallow matter and light. They shape the evolution of galaxies and may even play a role in information paradoxes. The famous Hawking radiation theory, proposed by Stephen Hawking in 1974, suggests that black holes emit a tiny amount of thermal radiation due to quantum effects near the event horizon. Over astronomical timescales, this could lead to the black hole evaporating, essentially collapsing spacetime slowly. However, this raises deep questions. What happens to the information of the matter that fell in? Is it lost forever, violating quantum laws, or somehow encoded in the Hawking radiation? This unresolved issue, known as the black hole information paradox, is a central problem in theoretical physics. If we could solve it, we might finally understand what happens to spacetime and reality when it collapses beyond our current limits of knowledge. Theoretical implications and speculative scenarios beyond observable physics. The collapse of spacetime opens the door to many speculative yet mathematically plausible scenarios. One such idea is that singularities may not just be the endpoints of spacetime, but also gateways to other regions, possibly even other universes. The concept of a wormhole, or Einstein-Rosen bridge, suggests that a black hole might be connected to a white hole, a region where matter and information erupt out instead of falling in. If such structures exist, they might allow for inter-universal travel or even time travel. Although these ideas are still highly theoretical and plagued with stability issues, they would require exotic matter with negative energy density to remain open. Another possibility is that a collapsing region of spacetime could lead to the birth of a new universe, an idea explored in cosmological natural selection and bounce models of the universe. In these theories, our universe could be the result of such a collapse in a parent universe, where a black hole's singularity becomes the seed of a new Big Bang on the other side. If true, this suggests a multiverse where each black hole collapse spawns a new, causally disconnected cosmos. Furthermore, some physicists speculate that a complete theory of quantum gravity, perhaps through string theory or loop quantum gravity, may resolve singularities and describe spacetime as a network of quantum interactions, eliminating the notion of collapse altogether in favor of a more discrete, stable structure. Ultimately, the collapse of spacetime isn't just a catastrophic event. It's a doorway into the deepest mysteries of physics, time, space, and existence itself. Whether it's through a better understanding of black holes, the development of quantum gravity, or the discovery of higher dimensions, exploring what happens when spacetime collapses may be the key to understanding where we came from, what we are, and what lies beyond the known universe.